Hello, algebra. Unit 2 still. Today, we're doing one of my favorite things when solving systems of equations called elimination. It's exactly what it sounds like. We're going to take a system of equations, which is two or more equations, and solve them by eliminating a term. Okay? Let's play. Maybe. There we go. All right, let's investigate how adding or subtracting equations can help us solve systems of linear equations. Okay, what do you notice? What do you wonder? Okay, stare at these for a minute. These are hangers. We have shapes on the left side and shapes on the right side. What do we notice? What do we wonder? Well, if I start at the first hanger, I have two circles. Oh, I'm in red. That's hilarious. And a square. Right, we've taken away a circle and added a triangle. We've taken away the square and added a pentagon. Pentagon. Okay, now here, from the first or second to the third, we added two circles and added a square. It's a lot of junk. So what do we notice? What do we wonder? I love the discussion in the classroom with these. I notice that between the first hanger and the second hanger, well, no, I notice if we add these two hangers together, we get this hanger. So I have two circles and one square, two circles and one square, one circle and a triangle, and a pentagon. Two circles, three circles and a triangle, and a square and a pentagon. Okay, I noticed that I added all those together. Sorry, apparently my device is slow. I'm going to pause you for a second so I can plug this in. All right, so that's what we noticed. All the hangers are balanced. Okay, this is not just a trick of us and drawing. These hangers are balanced, just like a balance beam. I don't have more weight on one side or the other. The weight on both sides is the same. Silly things like the circles are always on the left side, the pentagon and the square is always on the right side. There's a triangle on the left side of just the second and third. I wonder how much each shape weighs. If it's balanced, I wonder how much each shape weighs. Is the circle the lightest shape? No idea. Yeah, that's it. Now that we have a list of things the class noticed and wondered, is there anything on the list that you're wondering about now? How does this relate to math? Is one I'm assuming you would say. How does this relate to math? What do you notice about the left side of the last hanger? What about the right side? All the circles and triangles are on the left, and the square and pentagon is on the right. That's what I noticed. If we only saw the first two hangers but knew that the third hanger was a combined weights from the corresponding side of the first two hangers, could we predict whether or not the weights on the third hanger would balance? Yes. If the first two hangers balance, and we just added those together, then the third's also going to balance. There's no way for it to become out of balance if everything was balanced in the first place. Okay? All right. Let's get into some fun. Diego is solving this system of equations. Remember, a system is more than one equation hooked together with this nice loopy bracket. So here's his work. We have 4x plus 3y equals 10 and negative 4x plus 5y equals 6. And we are adding them together. I don't know why that addition sign is over there, because that's just weird. The addition sign always goes on the left. Looks like we're adding them. So I have a 4x and a negative 4x. I add those together and I get 0. 3y plus 5y equals 8y. 10 plus 6 equals 16. And then I'm going to divide both sides by 8, and I get y equals 2. Then Diego goes back to this equation and substitutes the y equals 2. 3 times 2 is 6. Nothing else changes. Subtract 6 from both sides. I get 4x equals 4. Divide both sides by 4. X equals 1. So my answer is 1, 2. Or just x equals 1, y equals 2. Okay? So we just talked through what did Diego do to solve the system. And is the pair of x and y values that Diego found actually a solution to the system? How do you know? Well, I know because I can plug them into the beginning. 4 times 1 plus 3 times 2 equals 10. That's a 2. 4 plus 6 equals 10. That's true. And I can try the second one too. Negative 4 times 1 plus 5 times 2 equals 10. I have negative 4. Equals 6. Negative 4 plus 10 equals 6. It works. So that ordered pair, what Diego solved, is a solution to the system because I substituted them back in and it was a true statement. Okay? Does Diego's method work for solving these systems? Be prepared to explain or show your reasoning. So I've got a system, and what Diego did is he just drew a line and added them together. And add straight down like you learned when you were younger. 2x plus 1x, there's always a 1 there, equals 3x. Y minus y is 0. 4 plus 11 is 15. Divide both sides by 3. I have x equals 5. Substitute that back in to either equation. It doesn't matter. I'm going to pick the first one. 2 times 5 plus y equals 4. 10 plus y equals 4. Subtract 10, negative 6 equals y. Now I can plug those back into the original and check. I'll pick one of them. Let's see, I'll pick the second one since we used the first one to solve it. 5 minus a negative 6 equals 11, which is true because that's plus plus. So it works. Okay, how about this one? Can I add them together? Well, if I add them together, I get 8x plus 8x equals 16x. 11 plus 1 equals 12y. 37 plus 7 is 44. I didn't eliminate anything, so that doesn't work. Well, what do we do? My goal when I'm trying to solve something by elimination is to get two terms that have the same leading coefficient, like an 8 and an 8, but opposite signs. All right, so for this one, what I'm going to do is subtract. And what's sort of silly about me and my head, I don't like subtracting because I tend to make silly mistakes when I subtract. So the first thing I'm going to do is multiply the bottom equation by a negative 1. All right, so I just multiplied the whole second equation by a negative 1. And now I can add because I like adding. Adding is easier. So let's add them together. 8x minus plus a negative 8x is 0x. 11y minus a 1y is 10y. And 37 minus 7 is 30. divide both sides by 10. I have y equals 3. Okay, pick an equation, plug it back in. I'm going to pick the first one again. 8x plus 11 times 3 equals 37. 8x plus 33 equals 37. Subtract 33 from both sides. 8x equals 4. X equals 1/2. So I have my two solutions. Let's double check that they work. So I'm going to plug it into the first one. 8 times 1/2 plus 11 times 3 equals 37. So this is going to be 4 plus 33 does in fact equal 37. We're good. So you see what we did there? The first equation, we were able just to add, and the y term was eliminated. But look what's different. The y term, the number in front of the y, they're both 1 for each term, but my signs are opposite. So I can add them and they disappear. They eliminate. My second equation, these are both 8s, but they were not opposite signs. They were the same signs. So if I multiplied the entire second equation by a -1, then I get opposite signs and I can add. Or you can go ahead and subtract. It's up to you. Why does adding the equations work for solving the system with 2x plus y equals 4 and x minus y equals 11? Why does that work? But it doesn't work for 8x plus 11y equals 37 and 8x plus y equals 7. Well, because for the first system, I had opposite signs with the same coefficient. In the second system, I have the same sign with the same coefficient. What if we subtract the equations? We did, okay? Would that help us solve the last system? Yes, that's what we did. How is adding the two equations here like and unlike combining the shapes in the two hanger diagrams earlier? Let's look at the hanger diagrams again. If we come back here, what if I take this system and subtract this one? So I'm going to subtract a circle and a triangle, and I'm going to subtract the pentagon. And I'm left with 2 circles and a square, which is 2 circles and a square. So I subtracted them and I got back to the beginning. So adding and subtracting, it doesn't matter. Your systems do stay balanced and you can still solve the system. All right, here are 3 systems of equations you saw earlier. System A, System B, System C. We're going to work through some of these. For each system, use graphing technology to graph the original 2 equations in the system. Then identify the coordinates of the solution. All right, let me get those actual equations in front of me because I'm going to switch over to Desmos. There we go. Hi. So 4x, you have this in front of you, 3y equals 10, and -4x plus 5y equals 6. Where they intersect is my solution. So go ahead and write that down, 1, 2. Okay, the instructions say, use graphing technology, identify the coordinates. Now let's find the sum or difference of the 2 original equations that would enable the system to be solved. I'm just adding them and I get 8y equals 16. Y equals 2. Okay, back to Desmos. I can type y equals 2. I can type 8y equals 16. It doesn't matter. And look, where both these green and purple lines are on your graph, it intersects the original 2 lines, the red and the blue, because it's part of the system of equations. It's part of the solution. So those 3 intersections, technically the 4 intersections, all intersect at the same spot, the 1, 2. So that's find the sum or difference. We got y equals 2, and then graph the third equation on the same coordinate plane. Make an observation about the graph. They all intersect at the same spot. Let's try another one. Let's add these together. 3x equals 15, x equals 5. Let's graph all 3 equations. Let's graph the system and then the x equals 5 and see what happens. Two x plus y equals 4. X minus y equals 11. Okay, that's the way down here. 5, negative 6. And then I got x equals 5 when I added them together. And they all intersect at 5, negative 6. It's pretty cool. I think it's kind of like magic because, like, what? They all intersect together? Yes, they all intersect together. It's pretty cool. Okay, let's just do system C. You've got it written there in front of you. And we'll do the math in a second. This is the one that we did where we had to subtract or multiply by -1 and add, because your teacher's brain works better that way. And I assume some of yours do too. Oh, solution's under my head. Okay, let's go back to the work. Okay, I multiplied everything by -1 and added. And I got 10y equals 30. Coming back here. 10y equals 30, which I could also say y equals 3. And my solution is 1/2, 3. So cool. All right. So what do you notice about the graphs? They all intersect at the same ordered pair. Why do you think the graph of the new equation intersects the other 2 graphs at the same point? Because it's the solution. Where graphs intersect is the solution. Okay? It's really not magic. All right. So lesson synthesis. Look at a system that you would have chosen to solve by substitution. Would you still choose to solve it by substitution? Why or why not? Well, here's the cool part. You guys have learned to solve by graphing. You've learned to solve by substitution. And now you've learned to solve by elimination. Okay, if I look at system 2, for example, this second equation is already solved for y. So substituting that second equation into the first equation for y may be easiest for some of you. Okay, and go for it. You can solve that by substitution. It's going to work. So substitution may work easiest for system 2. System 1, it's already lined up for us. And look at this n term. They both have a 1 in front of the variable, and one's positive, one's negative. So if I add those together, that n term is going to eliminate. So elimination may be easiest for system 1. System 3, okay, I can't add because I would get 10x plus 15y. Nothing eliminates. But I could either subtract or multiply the second equation by a -1 and add. So elimination is going to work best for system 3. So what we're going to practice is which system works the best and why. Okay, why would I choose one system over another? So I can solve system of equations by adding or subtracting them to eliminate a variable. You can. I know that adding or subtracting equations in a system creates a new equation where one of the solutions to this equation is the solution to the system. We added and subtracted equations, but it's still the same system. It still works. And our new vocabulary words, which will be in your glossary. All right? Good work today.